little dots there. There are two stars there. One is the one that's dying. The other hasn't died yet, will probably emit its own gas cloud in the future.
R.I.P. Southern Ring.
Exactly.
Professor, thank you so much for helping us understand this. And I have to say, I'm so signing up for his class as soon as I can.
I will say you have job security, though, because I understand, I feel like just a speck of this. It's so important to have you here to break it down for us, Brian. Thank you.
My pleasure.
Tiger Woods is...
Okay, my friends, it's just another day in paradise for Roger. Now I'm looking at the Webb Space Telescope, and they are working in the infrared range, which is a light range that we can't visibly see. We see light at a certain frequency. However, the same particle that creates light that we see is the same particle that creates every other ray, which is infrared, ultraviolet, gamma rays, everything. It's just here's the story. Light spins in a circle, and I'll show you this, no question whatsoever. And not only that, it is a particle, and I will show you that, no question whatsoever. So as it spins, it impacts what's in front of it. Now, if it's spinning slowly like this, you know, around and around and around, but very slowly, it's a red wave. If it's spinning like this, when it impacts, it's a blue wave. Well, what is the blue different from the red? Blue means it bounces back harder. That's all. This is coming this way, it's going bump, bounces back. This is going zzz, pow. Now, it depends on what it hits, just as much as it depends on the color of the light, because if it hits into something black, it'll more likely be mostly absorbed. So you won't see that radiation come back at you. Whereas if it's something in a lighter range, you see a brighter color come back at you. And all it depends on is the orbitals around the nucleus of what it hits. Well, what is the orbitals? Well, you have a nucleus of every atom. Every molecule has atoms, and the atoms have a nucleus, which is the core of the atom, and then it has a cloud of electrons. If they're way out here, and it gets bumped, you get pretty much red, because there's just a cloud. It goes poof, poof, and bounces back. If it's way down here, very tight to the nucleus, and it hits, it goes boing, and just shoots back like a bazillion-ton spring. Okay, way out here, it's just way out here, and it goes boing and bops back. But if it's way down here, it goes bing, because this one here is held tighter than hell. When you break them off of the real close ones, you get some power. That's why hydrogen is so explosive. It's all it is made of electrons. It's made out of these two particles, just like that, in a mass of about 1836 or so of them in a ball. And then one more of these same particles, a dipole, black and a white, wants to get in. The white wants to get into the dark core of the center. And it says, no, you cannot get in. All right, you can stay right out there. That's as far as you can get. And there's 1836 of them here, or 1835. And it wants one more to become 1836 neutral. Well, it can't get in there, because all the white ones surrounding that black core say, no, well, there's enough white ones, you stay out there. You can stay right there. Now, if you inject a spark in here and you interrupt this stability, everything blows. All the particles go at the same time, and the explosion is just horrendous from hydrogen. All right, now, I'm trying to make this as simple as I possibly can so that basically anybody can understand it, because it is understandable by anybody if you take the time to look at it. And that's what we're going to do right now. We're going to take the time to look at it. And the particles we're going to be looking at are those little black and white ones right there. and you see their orientation, they spin this way. They don't tumble like this. This has really got me freaked out because I can't understand how it's possible. Each one of these is a wave, which is basically one of these. All it is a up and down cycle, which means here, but it's a spin of up and spin to down, and up and down of the spin. So that's the up spin, and then there's a back down, a down spin, and we're catching it in the middle because it stays in the middle, and the field somehow pushes it because we had a field pushing it. Because they spin this way, but they also spin this way. This is very interesting because basically, now that I'm thinking about it, the planetary spin is very similar. This freaked me out, and I still have no idea about it yet right now. Because I'll show you how light spins. It spins in a circle. Now, why wouldn't this go up and around like this? It's at the leading tip of the circle spinning. Very, I need to talk to some people about this. I need an analyst. All right. This is the leading tip of a spinning light disk. And this is from red pulse laser. Now, Rod Warren did all these shots. Fabulous. For over a number of years, we worked together on this. Now, this, I'm not sure whether he was looking straight in front of it or this is the projection on the wall, but it doesn't matter. You can see that it's spinning. Now, the particle is at the tip. Now, here's the key. The particle goes straight up and down. You see how it's straight up and down here? It's not going to spin like a circle. It doesn't spin in a circle. It stays straight up and down. But this spins in a circle. This is what's got me freaked out. It's got to be ahead of that circle and just being pushed away without, for some reason, interacting with the spin, which has me a little bit confused. Because what I'm saying is, instead of this particle going spinning along with this spin, it's just going straight forward. But as it goes straight forward, the white part, well, actually it's this particle here, and it's going this way, not this way. It's going this way. So as it pushes forward, the leading glow white one will start to glow, and eventually it'll flip like this. And then this trailing white one will start to glow, and then it'll flip like this, and it'll flip like this, and it'll flip like this. This one spins this direction, but the light overall spins in this direction. Extremely interesting. Alright, so just to reiterate, this is the direction of the spin, but the particle spins this way. So this spins the light, each one of these is away, but the particle spins in this way. Now, strangely enough, I think that's planetary motion as well. Alright, I've been talking about push to shove, and this is what you see here. As this spins in this direction, see it tightening this way? It's crushing its field into the center, and the arms that stick out they consist of particles, and they're crushing into oncoming particles that are surrounding the world or the universe. So what happens is they bend backwards, plus they concuss, causing push to shove glow, and then that will push to shove the next pile of them behind that, and they will create these what they call interference patterns. They're not interference patterns, they are pushing and shoving each other into formations. These are repulsion patterns. These push this way, and these guys try to push back, and they say, no, you can't push me, you can't push me, and they create this zone here. It's called the Casimir effect. Okay, I can make it extremely confusing, I can make it extremely simple. This right here, in between these plates, is what I call basically the no man's zone between the push to shove. This comes pushing, this guy shoves back, there gets a space in between. That's the Casimir effect. Now, if you look at this, all these different colors, these are in the very fast frequencies of light. So you have them coming real fast. So your Casimir effect is very close. As they get, longer and longer the wavelengths, the Casimir effect gets further and further apart. Basically, that's what it boils down to. Alright, I want to show you something here. This is the electromagnetic spectrum. All that is the same exact particle, which is this particle right here. Every one of these is the same particle, only they spin faster and faster. You see the spin rate on all of these and how low that is? When you get way out here to this is radio frequencies. This is backwards, really. It should be the lower frequencies are here. Anyway, trust me. This one here is real long. And they're just sort of lopping through there in the radio waves. You don't see these. And actually, if you go past the radio wave, you're going to get down into sound. Sound is nothing more than the same exact particle. It's just not fast enough to turn into light. Everything there is vibration, creates energy. And that's just exactly what Tesla said. He was the rightest guy there was. Now, so what happens as we come closer? It starts way out here. It gets tighter and tighter and tighter and tighter and tighter and tighter and tighter. And then you get to a range like in the infrared, which is what they're looking at, which is just before our visible spectrum. So here they are here in the infrared. That's what they're using in this Webb. Now, up in here is where we are. But we only are in about this much of a frequency range that we can see, just a little tiny snippet. But that gives us all the colors we need because of the way our lenses work and our eyes and so forth. Now, these still have the same particles. Same particle, but now it's going zzz, and by the time you hit at the end, you almost have like a brick hitting you. There's no room in between. The gammas, they're just like, bam, it's just like a slam right into your face. So who's looking at what? Hubble was up in here looking at, basically somewhere basically in the visible light range. The Webb is below, so they're picking up particles that are coming through it. They must be increasing their energy level once they hit the Earth so they can pump them up to see the different colors. I'm not sure what they're doing with it, but all I can tell you is that this is the range of frequencies they're measuring. Now, anything coming at us is coming through all these gases. They show the gases and all the particles of light, which I've shown 1,000,000 times. So everything's slowing down. They have no idea looking in this direction how fast things or how far things are away, because they don't know how fast they're coming at us, because they don't know how much is in between. There's all kinds of particles and dust and magnetism and fields, and I'll show you this. I can show them better than they can. They look over in this direction, they may think it's going twice as fast, or they may think it's twice as far away, I'm sorry, but it could be right next to you. They have no idea because they have no idea how to measure the density in space and the magnetic fields, because everything pulls on these strings. Actually, I should say springs. It's really spring theory. And because that's what happens. As this light comes at you, let's say it's this long. It bangs into something, boing, and then it bounces back. And what do? You see this coming back at you. That light particle hits and bounces back. And it bounces back from one of these. Boing. Now, if it hits way out here and boings out, it just goes beep, very slightly. But if it hits way down here, wham, it takes off. That's the difference between the frequencies of light that return to our eyes. Okay, I would like to challenge this statement right here. The universe is expanding, could be, constantly, could be, which means that as you read this, stars, galaxies, and quasars, superluminescent objects that act like cosmic flashlights, are traveling farther and farther away from Earth. Now, the crazy thing is that they would be traveling, we would be the center of the universe if this was correct, because everything's going away from us in every direction. Now, as they do that, the wavelengths of light they give off gradually stretch out. So here's what they're saying. Here we are on Earth. because all of this stuff is going away fast, when we see the light, instead of being here as blue or red or green, it's way out here, so now it's red. Because it's going away. So it shifts. I say no. It's red. I'm sorry, it's because everything's going away, the light we see as it goes away is shifted to the red. I say no. That light coming to us shifted to the red because of all the particles in between. So this could be right down here and it's shifted to the red because there's a ton of particles in between pushing it against itself to make it less energetic. Okay, I think I can show that this is not true by showing you blue shifting to basically a blue shift. It's just like a red shift, only it's a blue shift. Now, it says red shifting is stretching of light toward longer wavelengths that occur as light travels through the expanding universe. They're saying it's being stretched this way as it gets pulled away. And you can use it to gauge distance. Well, I say no, you can't, because it's not because it's being pulled away. It's because it's being concussed as it's coming towards the Earth and it's just slowing down. So some of it's so far away we're never going to see it because it just slowed down and it got absorbed. It's being absorbed. The energy is being absorbed as it travels further and further towards the Earth. So instead of being blue out here, it's getting green and then, and then yellow, and then it turns red by the time we see it. They call that the red shift. And it's not a red shift. Well, it is, but it's impacted by a lot of things. It could be going away. Yes, absolutely, it could be expanding. However, that doesn't take away the fact that it's clouds of dust and particles and light particles that are interacting with the particles coming at us. So they're slowing them down. They shift red. Just like this blue will. Watch this. Now check this out. This is sizzling hot coming out of the Venturi. You see how close packed these particles are? And you see how they're starting to spray open slower and slower. It's still spinning. It's still spinning. But now all of a sudden we can see there is two particles, not just one. You see out here two particles, not just one. Here you really can't tell. Blue is so powerful. It's just stunningly powerful compared to the red and the green. The green is very, very powerful as well, but the red is not. And I can show you the difference between the red and the green. Watch. First of all, you saw the blue. It had two white little dots. That's the same as the green, same as the red. That's a photon. And once again, that's the new model is a dipole electron flood. The photons are nothing more than two electrons. One of these on each side is an electron. It consists of a muon neutrino, electron neutrino. We always considered that just an electron. The only thing we could ever see is the bouncy part, the glowy part. This doesn't bounce, it's hard. And when that bounces and squirts through our Venturi, we can see them squirt. This can't get through. Simple as that. When they come up to the Venturi, they're spinning just like we see here, and when they hit the Venturi, they just explode and divide. And this, of course, is the red, which is the same particle, identical same particle. This is the leading tip of the pulse red laser. And this is all one shot, picking up the same particle at the same time, because they're so fast, you get a whole batch of them. Just like you saw the blue, that was all the same particle. Now, what are we looking at here? We're looking at the same particle coming in, spinning. All right, so it's spinning in its circular way. Although these spin in this way. Don't forget, that's a little crazy to me, but it's starting to make sense. So as this spins, it's pushing this particle ahead of the spin. When it hits there, only, again, it's coming in like this, you can see it. But it's going to spin this way, and it's going to spin this way, and it's going to spin this way. And when it hits here, the white just squirts right through. It just goes squirt like that. Zip right through. This is going to bam, 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 bam. So what happens? The black ones keep smashing here and pushing the white through our little tiny single slit Venturi. can't remember if I showed you this or not, but the green is identical, so no difference whatsoever. And here it is. You can see they always have that same orientation of that spin. They don't tumble, although we did get them to tumble one time. All right, this took me a long time to figure this out, but I think I got it. This is the extremely powerful, which is the green. That's much more powerful than the red. As you can see how dull this is and how bright that is, and how this comes through here. This was the ray of the laser beam. But you see this here. What is this? What's going on with that? And this was the red one. And then what you see down here, what's going on with that? Well, this is push to shove. Again, this comes through and forces its fields that were surrounding it. Just like, remember I showed you the red field surrounds it. I'll show you again if I didn't. So this field pushes into this field. Well, the red gets out of the way because it's weak compared to the green. So it pushes the red away from its beam, all of it down this way. In addition, because when they come through, they're coming through like this. They're spinning like this. They don't spin like this. But now they are. Why did that happen? Because this one's coming through this way in the red. Da, 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 da. Nice having a nice day. This comes, and it bashes into one of these white ones and makes it spin like this. That's why you get that. It never happens. It just doesn't happen. And it's because of the orientation of the magnetism of the Earth. It'll always keep in this orientation. They call it upspin and downspin. When they see the white on the downside, it's downspin. When they see the white on the upside, it's upspin. You know, depending upon which direction it's going. And one, it'll charge up, and then it'll discharge. And it'll charge up, discharge, charge up, discharge, charge up, discharge, as they bang into the particles in front, just as I will show you with the red. Remember, particle-wave duality. Here's what it is. Each one of these is a pulse of the laser. It's on and off for an instant. In the front here is these particles. And there's more than one of them. There's a ton of them in there because light there's a lot of them at one time. But they're all coming forward spinning just like this. What happens here is the concussion of the huge magnetic field that surrounds. The field is huge, gigantic. These are tiny. They're in like these little dot ranges here. But the field is enormous. And that field is pushing these guys' fields away. So anytime you have push and shove, you have glow. The pushier, the denser the particles pushing, the glowier the glow. The less dense, the less glowier the glow. So these are basically electrons and heat particles and so forth. They just got to get out of the way. The gases and so forth. Now, so that's what causes the tip of the leading edge to glow. And this was taken right. This is the first pulse of the laser starting to take off, going through the air, heading for the Venturi, knowing that it has to accelerate to get through that Venturi. All right, so what have we seen so far? We've seen pulse, 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 a huge magnetic wave, tiny little particles in the center. Well, what is this? What the hell is going on here? That is that particle. That's this particle right here. And it's being sucked out of here so hard, so fast, that these are starting to glow because they're interacting much harder with these particles that are in front. That's why they're starting to glow a lot. They're not glowing back here that much. You see them back here? Not much. Up here, they said, get out of the way. Now, this is a photonic boom. This is exactly like a sonic boom, but it is in the photon range. It's identical. It's exceeding the speed that it's allowed to go, which is the speed of light. What happens here? They glow like hell. And when they hit here, they separate. The black cannot get through the slit. The whites can get through because they're being bashed through there. This one goes just like this. It squirts right down to nothing and goes right through there. This one keeps coming. It goes bam, 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 bam. And that's hard. That can't. That's a fixed particle. This is a squisher. It just squirts right through. That's what we have going on here. Now, what does that mean in practicality? That means we can accelerate light. We can show that light is a particle and a wave. We can show that light is made of two, what I call electrons, which would be An electron is this. One is the muon, the black. The other one is the electron neutrino, the white. We show that they can separate. That's fission. So all that stuff so far, plus the acceleration, plus the concussion here, plus the fission of the black separating from the white, that's sterile muons, and that is electron showers, and they come right back together here. And these are where all the Higgs fields appear. All right, in a second we're going to look up what electron volts are and how many electron volts are in light versus this interaction. You could see with your own visible eyes, there's just absolutely enormous amount of energy here, and we did zero to increase it other than create a venturi, which is just a really tight crushing device that makes the fields crush. The fields are huge. The particles are almost non-existent. But if you make the tiny slit where the fields are funneled in there and then you just slam them with the black particles, it's just going to bam, 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 bam. All these black ones, they can't get through. But the white ones can. And then you have what they call interference patterns, which this is only single slit. So forget all this stuff. Forget everything you've heard about quantum, because you can't. You have to start with electron flood theory. Shown it hundreds and hundreds of times. That's all that exists. Two of them together make a photon. They can be divided. Everything is made of these particles. Forget all that zoo nonsense and all that standard model stuff. These are what they call the gauge something or other particles, which is not, and they cause the Higgs. And I'll show you. We want to see some cool Higgs. This is amazing. All right, this is from CERN. What they do is hit particles head on, and they get all those white, extremely brilliant white, and then they form the Higgs right here. Where do you see our Higgs? This is just a little doodle. Where do you see this? Boom. This was a mind blower. Look at this thing. Exact same thing. Only we sent ours through a venturi. All we got is white. And when they hit, look at that. Isn't that spectacular? Absolutely spectacular. Okay, they're going to have to talk to us, Rodney and me, about these interactions. They've seen the particles, they just don't know how to make them, because they're using protons, smashing huge particles everywhere. All they're taking is balls of these and slamming them together and seeing all these little debris. You're going to see all kinds of things. They're going to see things like this. They're going to see things like that. They're going to see things like this. And they're all going to say, well, let's find the tiniest ones that exist. And they will find photons and protons and muons and electron neutrinos, and then they're going to find some exotic little quirky things which are in the very small range, and they see them enough times, they think they're in their particle zoo. The only thing that it should be in their zoo is these two particles right here, which is the muon neutrino and the electron neutrino. And, as I have shown, they can separate. Here's the way they normally will appear, virtually always, unless they're in their electrical form. And in that case, all you're going to see is one black and one white. That's an electron. And as they get bigger and bigger, the black goes to the center, the white coats it. That's why all we ever see is the bump of the white come back at us. Now, CERN, I think, and Fermilab agree. Because this is what they say they're looking for, the muon neutrino attached to the electron neutrino, which it was, and then they separate, which they do, to a shower and just a black muon. If you see a difference there, I'd like to know what it is. I mean, we can shoot out Higgs all day long. We just squirt them out. And that's because we're coming out of Venturi, and that's the fizzy white part, and then bam! That's the fizzy white part, bam! And this is the bam! And this is the head of the bam. This is, it's a photonic explosion. It's a photonic boom. Instead of a sonic boom, it's a photonic boom. And this, we should be able to harvest scads of electricity free. So why was I so specific about scads? Well, light coming from laser is light. To create electron volts, visible light photons, which is nothing more than we have here, it takes about 1.5 to 3.5 electron volts to make visible light photons. That's in a real weak range. Let's say we want high energy diagnostic medical X-ray photons, really powerful stuff. Nothing even close to here. We're way down below that. Let's say we're at 20,000 electron volts, because that makes color TVs work, 20,000. Let's say we're 100,000. Let's say 100,000 electron volts. Guess what? When you can make cosmic rays, which is exactly what we made here, the muon and electron neutrinos are cosmic rays. You're in the trillions of electron volts. To me, that is scads more than what we started with. That means free energy. And it could be as simple as this right here. And these are off-the-shelf components. You see that? That's the enhanced Higgs fields. But that's real. This is absolutely exactly what the picture was that was taken. Using the same technologies they're using, which is high-end CMOS stuff. Okay, once again, cosmic rays are nothing more than these particles right here, which are the tips of the Higgs. This is the actual true Higgs field, not a doodle about it. And these little dots seem to show the dark matter within the white glowy matter. You see how exquisitely patterned this stuff is? Even like here, something in that interaction in these borderline areas. But if you stand way back and look at this, it's phenomenal. And that is literally taken from the pictures that Rod took of the Higgs fields. And Fabien Boulez enhanced them the same way he enhanced the photons. All right, you see this? You would never ever see, well, maybe you would, maybe you wouldn't, but I didn't. I didn't notice that wasn't as bright as that. All right, I didn't see that. And I would never see any little particles down here sort of hanging around down in this area, but you can see them here. And you can see this is glowier than that. And what happens is this is interacting with those particles there. If you can see those little particles, you see them? He picked those up with his technology. I don't know, he's a pretty sharp guy. And so he's the one that enhanced these. Rod took the pictures. I understand the atomic nature of this. I've understood it forever, that it had to be a dipole. Everything has to be dipoles. You cannot have a singular polarity forever. Which everything we have here, they're just laying around here, they're not falling apart. Well, you can't have particles like one of these and one of these separated from each other for long durations of time. I don't think, but I got to be honest with you, I'm not sure. In outer space, they may completely surround the black particles, and the black particles may completely separate. Because I saw that in a Russian experiment. Let me just show you that. I'm going to leave it at here for now. But I'd love to interact with some of the people that have these exotic equipments and ability to do these kind of, looking at things in a different way. And maybe I could take a look at some of the stuff they have. Because I think I understand it pretty well now. And they're dipoles. Dipole flood theory is the only thing that works. Only thing. And they will never get anywhere trying to stay with the standard model. It doesn't work, never worked, never will work. Okay, I'm just going to leave it at this. These are the same particles Don Lincoln's been looking for. We found them. Muon neutrinos, electron neutrinos, sterile muons, electron showers. We can get free energy if we can get just to take a quick peek at this. Give us 60 days, 90 days, a few engineers, very limited budget, and we could find out if this works or not. I have people that are talking about doing it, but nobody's ever stepped up to really do it. We need somebody to do it, just to take a look at it. If it works, it works. If it doesn't, it doesn't. But I think it's going to work. So what am I showing you? I'm showing you muons, which is the biggest thing in physics, and I'm showing you separation of the muons from the electron neutrinos, a bigger thing, and I'm showing you sterile muons and electron neutrinos turning into electron showers, and in addition to that, we are now looking into space to see what are these particles in space, what do they consist of, why do they act the way they act. I know why they act the way they act because of these magnetic fields that surround the particles that I just showed you. Okay, which are these particles here. They have extreme magnetic fields around them, and that's why only the white can squirt through. Stay with me, you're going to see what we need to understand before we can do anything in outer space. Alright, seriously, what I've just shown you here, this is dark matter. That's heavy, it doesn't radiate, it doesn't absorb, it doesn't emit, it doesn't do anything but its gravity. It pulls the white right back to it. And these are normally solidly attached. And when we created sterile muons and electron showers, that's when we broke them apart. That's called fission. So don't forget, if they don't understand what light is, and they don't, they're never going to understand what all this means and how things push and shove each other and what these particles are. And now is the time to start talking about it. Everybody's talking about, right down the line, about Webb. Let's talk about Webb's web. Okay, let's just leave it at this. I have found the muons, electron neutrinos, Fermilab, CERN, and all of them are looking for Don Lincoln and his crew. There they are right there, sterile muons and electron showers. So, if we can use them to get free energy, that would be pretty nice. However, I'm basically excluded because I'm not peer reviewed. I think somebody's got to change that. I can't.